Let's say you were to feel and compare three different objects, an aluminum sheet, foam, and wood. Which surface would you consider to be the coldest? I will give you 30 seconds to feel each object, starting now. Now if you answered with wood, you are certainly wrong. Now if you answered with foam, you are 100% wrong as well. This means that the aluminum sheet was right? No, it was also wrong. You might be asking to yourself, what? Clement, are you crazy? You're the right person to teach about thermodynamics, but the aluminum sheet felt the coldest. True, but there is no such thing as cold. What exactly is cold? Okay, let's say I grab this cold ice pack and put it on my warm hand. It feels cold, but when something feels cold, that means that this object is taking away heat from me. Cold is defined to be the absence of heat. Therefore, in this example, there's an absence of heat in my hand. It feels cold because the ice pack takes away the energy from my hand. So when you were comparing the three different surfaces, you're actually comparing which surface took the most heat from you. In this case, the aluminum sheet took the most heat from you. Why is that? The reason why the aluminum sheet took the most heat was because of its specific heat. Specific heat is the amount of heat needed to raise the temperature of 1 gram of any object by 1 degree Celsius. Huh? What does that mean? I'm so confused. Well, don't be. For example, aluminum takes more energy to be heated up, as where copper can be easily heated. Now, in this case, since aluminum takes more energy to heat up, it actually has a higher specific heat than copper does. More heat is needed to raise the temperature of 1 gram of aluminum by 1 degree Celsius, as where less heat is needed to raise the temperature of 1 gram of copper by 1 degree Celsius. The rule of thumb is that the lower the specific heat is, the less energy it needs to be heated to a certain temperature. But because aluminum has a higher specific heat than the copper does, it is able to attain the energy within it more longer than the copper can. Let's say there were two pots with the same volume, but one was aluminum and one was copper. They were both set to 100 degrees Celsius, and then they were just let out to the open atmosphere at 25 degrees Celsius. What will happen is that copper will release its energy more quickly than the aluminum will. But in order to make sure you understand this, we're going to do some practice problems. If I were to heat a gold brick and a brass brick, a silver brick, all to 100 degrees Celsius, which brick will heat up the slowest? It is assumed that all the bricks were heated within the same environment and same conditions as each other. Hint: gold has a low specific heat and silver has a high specific heat. The answer was C, a silver brick. Since silver has the highest specific heat, it needs the most energy out of all three materials. Next question. If I were to heat a gold brick, a brass brick, a silver brick, all to 100 degrees Celsius, which one will hold its energy for the longest period of time if all of them were in an atmosphere of 25 degrees Celsius? Hint: gold has the lowest specific heat and silver has the highest specific heat. Answer was C, the silver brick. Since the silver brick has the highest specific heat, it retains its energy the longest out of all the options. Next question. If I were a chef, I needed a pan in which gains heat and loses heat quickly. My options for metals were copper, bismuth, and aluminum. I tested each pan within the same type of environment and I got the results. Which one should be the top pan for me? Hint: bismuth has the lowest specific heat and aluminum has the highest specific heat. The answer to this question is B, a bismuth pan. This is because the amount of heat needed to heat up bismuth is very little compared to the other options, since bismuth has the lowest specific heat.